Hello, welcome to my poster Near Real-Time Streaming Analysis of Big Fusion Data. Here I will briefly introduce you to our work on connecting fusion experiments and high-performance compute resources and how we aim to accelerate fusion workflows. By making data analysis results directly accessible to scientists that are working on experiments, we aim to improve and accelerate experimental workflows. Especially camera data, which are by far the biggest data streams, take a long time to analyze. But analysis of camera data can give a better understanding of the dynamics of a fusion plasma, for example by detecting and classifying modes such as magnetic islands. We are developing a framework that facilitates such workflows, streaming big and fast data to a remote compute resource, performing data analysis, and immediately provide the results to the scientists. We call the framework Delta. It is a distributed system that is deployed and executed on multiple systems. First, we have a generator that runs at the experimental site. Here I use the K-Star tokamak in Korea as an example. I've denoted that it runs on a data transfer node. That is just a node that is optimized for data transfer and usually has access to a high bandwidth wide network area interface. The task of the generator is to stage the experimental data for streaming and send it to the HPC facility. Delta uses the ARDIOS 2 framework for all I/O. ARDIOS 2 is a high-performance I/O framework developed specifically for HPC environments. Data streams where we use ARDIOS 2 are highlighted with orange arrows in the figure. Following the arrows from the generator, we arrive at the HPC center, in our case NERSC in California. The data stream is received by a middleman running on a NERSC data transfer node. The only job of the middleman is to receive packages from the data stream and forward it to a processor. Finally, the processor receives the data stream and performs data analysis on the distributed compute resource. The analysis results are then stored on a server that is accessible to externally facing services. At NERSC, this is either a dedicated file system or a database. The web server for the visualization runs on NERSC's Spin service, which uses Rancher to orchestrate Docker containers. The web server connects visualization requests from web clients to the database storage to provide the clients with analysis results in real time. Okay, let's take a look at how it looks when we run Delta. Here you see two rows of terminals. The lower rows show output of the Delta framework and the upper rows will show resource utilization. The lower left terminal shows the Delta generator running on the K-Star DTN. The lower middle terminal shows the middleman running on the NERSC DTN, receiving and forwarding packages, and the lower right terminal will show output of the Delta processor running on Cori. And then there's the upper row of terminals which show you utilization of the resources, the wide area network K-Star to NERSC on the left, the local area network NERSC DTN to Cori in the middle, and CPU utilization of Cori on the upper right. For the run we are showing here, we are streaming the output of the ECI diagnostic from one shot, which is about 5 GB of data. Okay, here we have started the processor and the middleman. They are requiring input for ARDIOS 2, where we are using the SST streaming protocol, and it's awaiting some connection information, which we have to copy and paste in the terminal to start the streaming. Now we are starting the generator. It loads the ECEI HDF5 data into memory and stages it for transport. Once that step is complete, it will provide the SST contact information for the middleman and for the processor. So now we have provided the contact information and we can start the streaming. We can see that the generator is sending to the middleman and the middleman is also forwarding to Cori. And right now the data stream is running at about 500 megabytes per second, quite reliable. and we see that the generator is almost done sending packages to the middleman. Now we are finishing up the streaming. We see that the processor has received all the 500 time chunks, and the pre-processing and storing in database took about 216 seconds. To take a quick look at the pre-processed ECI data that was stored in the database, we can use a web dashboard. Here we have to type in the name of the collection, select a time chunk that we want to take a look at, so we are picking one. Then we click on load data. That instructs the backend to fetch the data from the database and run some pre-processing. When the web server is done fetching the data and pre-processing, that is interpolating for plotting, it's accessible to the web client. In the plot, it's quite interactive and gives you a responsive plot of the ECI data from the requested time chunk. Okay, let me give a quick conclusion and line out our future work. The Delta frameworks facilitates reliable streaming of big fusion data from experiments to remote HPC centers. Analysis of data on distributed systems using either CPU. It facilitates storage of data in databases together with metadata. It also facilitates the real-time visualization of the analyzed data. We try to look at using machine learning algorithms to automatically detect and label MHD phenomena, for example unsupervised methods such as clustering or supervised approaches such as ConvNet for feature detections. We also would like to look at a tighter coupling to the data acquisition systems, such as to stream directly from the digitizers and completely bypass the file system. We are also And finally, we aim to explore the use of established stream processing frameworks such as Apache Beam. That's it. If you want to check out Delta, visit the link on this slide or follow the QR code. Thank you for your time. Bye.